In this video, we'll discuss present values of annuities. Now, it's important to recognize what's the difference between future value and present value. And as a reminder, an ordinary annuity is one that pays out at the end of each payment period. Now, as we discussed before, the future value is the total of all the periodic payments and all the interest that we earn in an annuity at the end of some amount of time. This is like paying into your retirement, into your 401k. We're going to look and say the future value is what will be in that 401k the day that you actually retire. In contrast, the present value is the sum that must be invested now in the annuity to guarantee some desired periodic payment for a given amount of time. So it's the idea here that when you retire, how much do I need to have now to make sure that I can make monthly payments of however much I want until, say, I'm 90 years old or 95 years old. So it's the other side of that where we're looking at what can the annuity pay out after it has that lump sum. So that changes some of how we look at the formula as well. Now, as a reminder, A is our present value. It's that lump sum that's in the account to start with. P is the payment at the end of each pay period. How much are we going to pay out from that present value? R is still interest rate, and T is still time, and N is still the number of times that we're computing in 1 year. And again, remember here that we're looking at payments. How much can this lump sum pay out? We'll still have the same potential computations for each of the annual times each year for monthly, quarterly, and biannually. But we need to pay attention to which variable are we solving for in a given problem. So say we have an unknown present value. What would an example of this look like? So when Karen retires, she wants to receive $4,000 at the end of each month for her retirement annuity for 25 years. If the annuity pays an annual interest rate of 6% compounded monthly, how much money will Karen need in the account before retirement? So we know here that we don't know what amount is needed, that lump sum to make this happen. We do know that we're trying to look at getting $4,000 payments. And we know the interest rate will be 6%. It's going to go on for 25 years into retirement. And we're going to compound monthly. And monthly means 12 times a year. So let's substitute in the values we have. Now, there's a lot going on here. Let's take it one piece at a time. I'm going to simplify my two fractions. And I'm going to go in and multiply 12 times 25 to get that exponent simplified. Now I need to raise to my negative 300 and then do 1 minus that value. And again, look how many decimals I'm carrying out. I'm trying to carry as many as possible all the time. Your calculator can handle that. You can use the answer key to help you pull it from one line to the next so you can keep your solutions as accurate as possible for as long as possible. Now I'm going to take that difference and then divide it by the 5 thousandths. Again, keeping as many decimals as possible. I multiply that by 4,000, and now I can round to the nearest hundredth because I'm looking at money. So I would say that Karen will need to have $620,827.46 in her retirement account to have a monthly payout of $4,000 for 25 years. So again, we're trying to calculate what's needed to make this happen in retirement. Let's look at an example of what if we don't know what the payout could be. So Malik recently inherited $300,000. This money was invested in an annuity that pays Malik semi-annually for the next 15 years. If the annuity pays an annual interest rate of 5.5% compounded semi-annually, how much will Malik receive from the semi-annual payments? So here, we know the amount that's there, the lump sum. It's $300,000. What we don't know is how much Malik will receive in each of those payments. We know the interest rate is 5.5% or 55 thousandths. We know that's going to happen for 15 years and that we're going to compound semi-annually. That's twice a year. So again, we're going to substitute in all our values we have, and then in this case, we're solving for P. I'm going to simplify my fraction as I did here and simplify my exponent. Again, now I'm going to raise to my exponent. I'm going to do the difference of my numerator. I'm going to divide that value by the denominator. And look, I'm keeping long decimals. Again, I can use that answer key on my calculator to help me. Then I can say I've got 20.2493013, and you may have more decimals than that, times p. To get p by itself, I divide both sides by the 20. And then I can round 2 decimal places, and that will tell me the amount of money that Malik will get semi-annually. So Malik will receive $14,815.33 every 6 months from the annuity for the next 15 years. We can also solve for time. We just have to be very careful as we go along doing this, because this pulls in concepts of logarithms. So the Warren family won the lottery for $1 million. Instead of taking the lump sum, the money was placed in an annuity that pays them $50,000 at the end of each quarter. If the annuity pays an annual interest rate of 7.5% compounded quarterly, how long will it take until the annuity reaches a balance of 0, round to the 10th of a year? Now, that balance of 0, we're trying to pay it out for as long as possible. So what this means is we have our lump sum, $1 million. We know the payout, which is $50,000 that's happening quarterly. We know the interest rate is the 7.5% or 75 thousandths. And we don't know in this case the time, how long this will take. But we do know that we're compounding quarterly. That's 4 times a year. Now, the until the balance is 0 means that we're going to pay out until there's nothing left. And that happens when time runs out. So let's substitute in our values and take this one step at a time. Now, like before, I'm going to simplify my 2 fractions. Now I see I can't do raised to the negative 4t because t here is an unknown. So I need to start working on the other parts. So this is $50,000 times this whole fraction. So I'm going to divide both sides by 50,000. That will leave me with 20. Now I can look and say, well, I've got a denominator. I'm going to multiply both sides by the 1,875 hundred thousandths. And that will leave me with 375 thousandths. Now I want to get the 1 away, so I'm going to subtract 1 from both sides, which gives me negative 625 thousandths. Now, since this is a negative and this is negative 1 times our value, I'm going to multiply both sides by negative 1 so that I can recognize that this is a positive on each side. That should look familiar because I have a number raised to an exponent. I have to think back, how do I deal with that with logarithms? That's where we are at this point. So I'm going to say that this is the log base 1.01875 of 625 thousandths equals negative 4t. Now, here, there's no button to put this in as my base for the log, so I have to use my change of base formulas for the logarithm. To do that, it's just take the natural log of what was inside my logarithm divided by the natural log of the base. When this simplifies, it gives me negative 25.30113446. I just pulled out every decimal I could from my calculator. Then I divide both sides by the negative 4, and now I can round that value to the 10th of a year and say that the annuity will reach a balance of $0 in about 6.3 years.